Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's presentation on sampling distribution, Part 1. In the previous session, we have discussed the introduction to sampling distribution, all the definitions required to understand the actual concept, and then notation, the formulae, and different types of sampling distributions. An overview of today's presentation. Today, I am going to discuss about degrees of freedom, standard error, and sampling distribution of means in two different cases, sigma known and sigma unknown. Now, let us recall the introductory part, and here we have defined two: population and sample. Population is the set of all objects under consideration, and sample is a subset of the population. Since it is impracticable or uneconomical or time consuming to study the entire population, we consider a non-empty subset of this population, that is called the sample. For example, the population of India is the main population and population of Telangana is a sample of that population. Next, sampling. Sampling is the process of drawing samples from the population. So, from where we got these samples? These samples are obtained from the population itself. So, there may be number of ways of drawing samples from the population. So, the process of drawing samples from the population is called sampling. That sampling can be of different types. Mainly, the sampling must be random sampling. So, that means each element of the population must have the same equal probability or chance of being included in the sample. That is called random sampling. Similarly, sampling with replacement and without replacement and all. And there are different types in sampling distribution, and the sampling distribution of means, and K, the number of population parameters which are calculated using the sample data. For example, using the sample data, we are estimating or we are calculating the mean of population, which is mu. If we are calculating mu using the sample data, then K equal to 1. For example, if we are calculating both mu and sigma, the standard deviation, then K will be 2. So, the number of population, K is the number of population parameters which are calculated using the sample data, and N is the number of independent observations. So, the degrees of freedom is a positive integer denoted by nu given by n minus k, where n the sample size and k the number of population parameters which are obtained from the sample data. And next, standard error. Standard error is the sampling. Standard error is the standard deviation of the sampling distribution of some statistic. Let us consider some statistic S. Statistic means any measurement, statistical measurement calculated using the sample data. For example, sample mean, sample variance, sample standard deviation, sample proportion, all these are statistics. Let us obtain the sampling distribution of some statistic S. That means the samples 1, 2, 3 and so on, and K samples for example, and let us find sample mean for all these K samples, then S1, S2, S3 and so on Sk. So, this is called the sampling distribution, and if we calculate the standard deviation of this sampling distribution, that is called the standard error. So, standard deviation of the sampling distribution of some statistic S is called standard error. As the sample size n increases, the standard error decreases. So, size of the sample and standard error are inversely proportional to each other. And standard error plays an important role in large sample theory, and also it forms the basis for testing of hypothesis. In testing of hypothesis, we use that standard error value, SE value. In particular, for means, it is standard error is sigma by root n. We use this in testing of hypothesis. So SE helps in learn information about the corresponding population parameters. So the standard error is the standard deviation of sampling distribution of some statistic. Now, in today's session, I am going to discuss about sampling distribution of means, in particular case sigma known. So there are two different cases in sampling distribution of means. One is sigma known and the other is sigma unknown. So we will discuss about sigma unknown in the next session. In today's session, I am going to discuss about the sampling distribution of means under sigma is known. Let us consider a particular case of finite population. Let us consider a population of size capital N. So that means the value of n is finite, so the population is finite population. So consider a finite population of size n with mean mu and standard deviation sigma. Now let us draw all possible samples of size small n from this population and then find the mean of all these samples and then arrange all the values in the form of a table. For example, the sample, different samples, yes, sample 1, sample 2, sample 3 and so on, k samples. Let us find the sample mean as I told you. So x1 bar, x2 bar, x3 bar, so on xk bar, where xk bar is the mean of kth sample. This is called sampling distribution of means. So here we have considered different k samples from the population and calculated mean for all these samples, and the set of these two values is called the sampling distribution of means. And if we calculate again the mean for this sampling distribution, if we calculate the mean for this sampling distribution of means, that is called mean of sampling distribution of means. Similarly, if I calculate variance for this sampling distribution, that is called variance of sampling distribution of means. So let us denote these terms by mu x bar, the mean, and sigma x bar is the standard deviation, where sigma square x bar is the variance. So mu x bar and sigma x bar are the mean and standard deviation of sampling distribution of means. Then these two values are given by, you see here mu x bar is mu. What does it mean? What is mu actual value of mu? This denotes the population mean or the mean of the population, and mu x bar is the mean of the sampling distribution of means. So here this mu x bar and mu are the same. In sampling distribution of means, sigma known, that too in finite population case, mu x bar is mu, the sampling distribution of means. Then the mean of sampling distribution of means and the actual population mean are the same. Similarly, the next one, the standard deviation of sampling distribution of means is given by sigma by root capital N into under root capital N minus small n by capital N minus 1. Here the term in this square root, that is called the finite population correction factor. Here the population is a finite population, that's why we are using capital N value which is finite, and small n is the sample size, and capital N minus small n by capital N minus 1 is called the finite population correction factor. So this is the case when a finite population is considered. The same thing can be expressed in another way as the sampling is done without replacement. The sampling is done without replacement. What does it mean? Without replacement means we cannot select an element of the population more than once. If we selected a particular element, we are not replacing it back, so we cannot again select it back. So that's why finite population case or sampling without replacement, these two are one and the same. So in this case, the mean of sampling distribution of means is equal to mu, and standard deviation of sampling distribution of means is equal to this value sigma by root capital N into square root of capital N minus small n by capital N minus 1. A similar case, let us consider the same thing, sampling distribution of mean sigma known, in that infinite population. So that means let us consider a population having infinitely many elements. or else the same thing can be considered as sampling with replacement. Suppose the samples are drawn from an infinite population, or the sampling is done with replacement. With replacement means each element of the population can be selected more than once. So, after selecting one element from the population, again we are replacing it back. So, we can consider an element as many times as we want. That means the population can be considered as infinite population. So, that means in sampling, if the sampling is done with replacement, that can be considered as sampling from an infinite population. So, these two cases are the same. In this case again, we construct the table, that means the sampling distribution of means, samples, different samples, 1, 2, 3 and so on, k samples, and a sample mean x1 bar, x2 bar and so on. And again let us calculate the mean of sampling distribution of means denoted by mu x bar. Similarly, standard deviation of sampling distribution of means, sigma x bar. So, mu x bar and sigma x bar denote the mean and standard deviation of sampling distribution of means. In the case of infinite population or sampling with replacement, this mean of sampling distribution of means is again equal to the population mean mu. That means in both cases this is the same. In the case of without replacement, mu x bar is mu here, and in the case of with replacement, mu x bar is mu. So, in both cases the mean of the sampling distribution of means is equal to the actual population mean. Whereas the standard deviation of sampling distribution of means in the case of with replacement is simply sigma by root n. There is no finite population correction factor. There is no finite population correction factor, since here the population is not considered as finite. Whereas in the previous case, we have this additional term, square root of finite population correction factor, and that term is not present here as the population is not finite, or the sampling is done with replacement. So, here this sigma by root n is called the standard error of mean, which we have discussed in the earlier slides. So, sigma x bar sigma by root n is the standard error, SE, standard error of means. So, these two are different cases in sampling distribution of means when sigma is known. If we have sigma, that means the standard deviation of population is given, then under two different cases like finite population and infinite population, or with replacement and without replacement. So, these are the cases in the for sigma is known. Similarly, we will discuss sampling distribution of means when sigma is unknown. Also, so sampling distribution of means sigma is unknown. If the population standard deviation sigma is unknown, simply we replace this sigma by the standard deviation of sample. When the sample is given, if a sample is given, that means we have the sample data, then we can calculate the variance S square, then positive square root of variance is called standard deviation. So, if sigma is unknown, simply we replace it by S. So, if the population of standard deviation sigma is unknown, then we replace it by the sample standard deviation S, and then the random variable x follows the t distribution with n-1 degrees of freedom. And here the t variable is defined as t equal to x bar minus mu by S by root n. In fact, what is Z? The standard normal variate, x bar minus mu by sigma by root n. So, if sigma is unknown, simply replace it by S, and it follows the t distribution with mu equal to n-1 degrees of freedom. So, degrees of freedom, that also we discussed in the earlier slides. And here this sampling, this standard deviation of sample can be obtained using this formula. Here the variance is calculated, S square is calculated as sum of squares of deviations. So here xi minus x bar whole square. What does it mean? Xi are the individual elements of the sample, x bar is the mean of the sample, and we are considering the difference between these two. So how the values are deviating from the actual mean. So xi minus x bar whole square divided by n minus 1. So sum of the squares of these values, that is given by s square, and then take the positive square root of this, that gives the standard deviation. So if sigma is unknown, simply we replace t. And the main important point is, particularly if the size of the sample is less than 30, that means the sample is small sample, then we use t distribution. If the sample is large sample, then we use z distribution. Even though sigma is unknown, you can replace here by s. Even though s is unknown, you can replace by sigma here. But if the sample is small, that sample data will be given. So using the given data, we can calculate the variance. From that, we can find the standard deviation, and we can use that in this formula. But the particular case is, for small samples we use t distribution, and for large samples we use z distribution. So coming to the summary, in today's session we have discussed a particular case of sampling distribution of means. There are different types of sampling distributions, like sampling distribution of means, variances, proportions, standard deviations, and so on. And today we discussed about the sampling distribution of means. In that particular case, when sigma is known, that means the value of sigma is given. What is sigma? The standard deviation of the population is given. Then again there are two different cases. Case 1 is for finite population and for infinite population. In finite population, since the population is finite, the sampling must be without replacement. And if the sampling is with replacement, that can be considered as infinite population. So the first case comes under without replacement, second case with replacement. And then another case, sigma unknown. When sigma is unknown, then we replace sigma by the sample standard deviation s. So these topics we discussed today, and in the next session we solve some problems, solving problems in sampling distribution of means, sigma known. So that's all for today's session, and we'll meet in the next session. Thank you.